Well, we're going to look at 1.2 exponent properties, and I'm going to go ahead and split this section up into sort of two. So we're going to have a 1.2a and a 1.2b when it comes to videos. So you can see the line. So objective-wise, we're going to look at the first four types of properties, then we'll look at the last four things in this section. So let's go ahead and jump in, look at negative exponents. When we talk about properties of exponents, what we want to do is there's just a lot of repetition with this. So, but we need to identify when we see these different types of properties. So, flashcards are going to come in handy if that's something that you utilize. But when we look at something like a negative exponent, we want to understand what a negative exponent actually means. And so, a negative exponent actually represents the multiplicative inverse of that base. So if the base is a and I have a negative n as its exponents, really what I'm saying is what is the multiplicative inverse of a to the n? And in the previous sections when we talked about our properties of real numbers, inverse was one of them. And the multiplicative inverse of a value is simply the reciprocal. And so that involves like flipping. And so that's what I want you to recall from something like this is that when you see a negative exponent, how do we make it positive? You flip it. Now that's a pronoun, this it. So what do I mean by it? The base with the negative exponent. So it's not necessarily everything. You have to determine what has the negative exponent so that you can flip that item. And so that is what a negative exponent is. It's an inverse, a multiplicative inverse, and we're just going to flip the base that has the negative exponent. So be very careful when you do this because it's not necessarily everything. Now we will flip things from, let's say it starts off in the numerator and then we flip it to the denominator and that makes our exponent positive. Or we have a base that's in the denominator and a negative exponent, and that allows us to take that base, move it to the numerator, and now our exponent is positive. Now, the skill of making an exponent positive goes in the other direction. And so if I did have, let's say, something like 1 over x cubed, and I said, okay, I want you to rewrite this, some equivalency. But this case, instead of making the exponent positive, what we can do is rewrite this as an exponent that's negative. Now, that skill right there, we don't utilize a tremendous amount in pre-calc, but next year in calculus, we do that all the time. And so we want to make sure that we're very comfortable with manipulating our exponents here using those properties. So whether it's making an exponent that's negative, making it positive, or for next year, making something that's already positive, maybe in the denominator, but rewriting it as a negative exponent. So we can do some things with it. That's why. So let's look at some examples of these, and that's what it takes. Right now, they're going to be pretty basic because we don't have all the other properties in. But let's go ahead and dive through them. And again, if you feel comfortable, you go ahead and start, and then just check them, pause, and then check it once you're done. So here, what we have is I have 2 to the negative 3. If you want to know what that actually means, what I'm asking you, it means what is the multiplicative inverse of 2 cubed? That is what this means. So a negative exponent does not mean negative at all. It actually means multiplicative inverse or inverse. We'll be using that type of notation for other things that mean inverse as well. But here it means multiplicative inverse. So flip the base. The base is 2. So instead of the 2 being in the numerator, the 2 goes to the denominator. So instead of 2 over 1, we bring the 2 down and it leaves a 1. But that allows us to make the exponent positive, which is our objective at this point. And then 2 cubed is 8, so 1/8 is that evaluation. Now, instead of a numerical base, let's see if it's a variable base. And so here we have b to the negative 2. Oh, I have a negative exponent. How do you make it positive? Flip it. What's the it? The base with the negative exponent. And that allows us to make our exponent positive, so we get 1 over b squared. Now, this is where we got to slow down just a little bit. When we look at something like this, hopefully you do recognize there's a negative exponent, but what has the negative exponent? Just the x. This is 3 times x to the negative 1. So the negative exponent is not attached to both the 3 and the x, like the example down here that we're getting ready to do, where it's attached to both. In this example, the 3 has nothing to do with that negative exponent. So it stays exactly where it is, which is in the numerator, and allows us to flip x to the first. We don't really need to put the 1, but it's there, down to the bottom and make my exponent positive. So you've got to make sure you identify what has the negative exponent. So much like this example here, what has the negative exponent is the entire bubble. So what am I flipping is the entire bubble. Now we're going to do something here. I mean, you know, it's a little bit beyond, but you guys have had in Algebra 2 and prior classes, even maybe even Algebra 1, how to handle 2x squared, the quantity 2x squared. So what we're going to do is we're going to square the 2, which is 4, and square the x, which is x squared. So it's called power of a product, and we end up using power of a power to, you know, when there's exponents in there, but we end up sharing it. That's how we do that. Looking at the next example here, I throw another negative like out front, but that negative is just a coefficient. So again, I see students, I just try to sort of throw some weird ones out there to try to see, do we truly understand what we're supposed to do to simplify an expression like this? This negative out in front has nothing to do with flipping anything. It is simply a coefficient that is negative. The flipping comes when there's a negative exponent, just like that. So I go, well, what has that negative for? Simply x. And so the x is going to get flipped to the numerator, and then the exponent becomes positive. Now, you don't need to put the 1 out in front, but the negative you can put out in front or you can put in the numerator, and then that 2 stays where it is. And so we get the opposite of x to the 4th over 2. Looking at the last example, now we have multiple variables and this negative coefficient. Again, the only thing we really are concerned about is that right there. That tells me I need to flip it. The other two items, the negative 2 is not, that is not an exponent, so there's no flipping. X to the 4th is just fine. It's just that that y squared needs to come up and join them so that we can make the exponent positive. So there's an example here that's maybe a little bit trickier of one. And the reason it's a little bit trickier is because the difference between this one and let's say the ones we just did is all of the ones that we just did are monomials. So I want to clarify that the property of exponents works for monomials. When we look at something like this and I see x to the negative 2 plus y to the negative 3, a lot of times what students have a tendency to want to do is simply take the x and move it down to the bottom and take the y and move it down to the bottom. But what you're doing is using a property of monomials in a binomial, and that is a no-no in math. And so it doesn't mean we can't make these negative exponents positive, but it's not, the negative exponents are monomials not within inside the whole expression here because of that plus sign. But I do have a monomial here and a monomial here. That's what a binomial is made up of two of those. Now, I say monomial, binomial. Technically, these aren't because they're not polynomials type of thing with variables being the denominator, but single term and two term. I'll go with that. That's better terminology here. So x to the negative 2, if all I did is just look at that bubble right there, if all I said is just simplify that, you guys would have no issue. You would take the x, you would move it to the denominator and make your exponent positive. If all I did is say take the y to the negative 3, ignore everything else, and simplify y to the negative 3, again, I would anticipate all of you doing very well at that is for that part. But what we have now is how do we connect these two with that plus sign, and then what we have is that 2 on the bottom. And so we get a situation where it looks like this, and this is a complex fraction. So it isn't a monomial. It's like a single term with two terms inside of it. So at this point, what we want to do, and I'm going to go a little quicker now, but to solve this complex, I need common denominators. So you got y cubed on top and bottom for those, and then you've got x squared on top and bottom for that. And then what we get is we get y cubed plus x squared. And then our common denominator is x squared y cubed. So keep it. So if you remember KFC or keep, flip, change, or multiply by the reciprocal, or any of those phrases that maybe your teachers early on, like in middle school or early high school, taught you how to handle complex fractions, what we do is we keep the numerator. In other words, don't do anything once it's a single fraction. Then we change the division bar to multiplication, but we flip 2. And so in this case, it makes it 1/2. And so what we end up getting is a y cubed plus x squared, and then over 2x squared y cubed. Now, even when we get here, it's tempting for some students to try to cancel y's. There are 2 terms up here. When we have multiple terms, you can't touch one of them without touching all of them. So the only way to cancel any y's out is if all terms have y's in them. In other words, both terms in the numerator and the term in the denominator. There has to be a common factor for you to cancel out. So please, really resist that temptation. It makes, I think, a lot of sense when you look at something like this and we get that right there. Just resist that temptation to try to cancel the x's out or try to cancel the numbers out or something like that, because it doesn't work like that. The answer to this is not -1, not even close. And so we want to be very careful not to um, you know, try different things in math without at least understanding, is there a property? Is there a reason why to do it? It has to make sense. Moving on, we have negative exponents first. So that is, how do you make negative exponents positive? Flip it. What's the it? The base with the negative exponent. Now we're moving to multiplying powers. Now, whenever we multiply powers, what we're saying is if I have two bases that are the same and I'm multiplying them, then I simply keep the base. Notice the base does not change. Base stays the same. But what we do is we find the sum of the exponents. So when you multiply common bases, you keep the base and you add the exponents. Okay. Now, if there are coefficients out in front, then you would multiply the coefficients, keep the base, add the exponents. So we'll see that in just a moment, like on the second example, where 3 and the 4 are coefficients. And so how do I handle that? And it's really, we do that through commutative property. But let's look at this first example. Now, I'd say most of us would probably do 2 squared 4, 2 cubed 8, and do 4 times 8, 32. Let's make sure we can get 32 using our property, though. If you notice here, we have common bases, and we're multiplying. So what that means is my base stays the same. Base does not change. But what I do is I take my exponents now and simply add them. And you get 2 to the 5th. And what we said the answer should be is exactly what it is, which is 32. Okay. Looking at a second example, bringing in variables now. But if I use commutative property and reorder this, I can put the 3 and the 4 right next to each other, and the x's right next to each other, something like this. Now we'll do this more in our head. We won't rewrite it like this. I hope you don't have to rewrite it like that, but that is the property. That's why we can simply do 3 times 4 and get 12, and why we can do x squared times x, and when we multiply powers, we add the exponents. Base stays the same. And so we end up getting 12x cubed for our solution for that one. All right. Now moving into the bottom left one, similar to that one, I'm just throwing a little bit more variables at you, kind of thing, just trying to get a little bit harder. But here I won't rewrite it. We'll just do 3 times -4, which is -12. This is not distributive property. It's commutative. We're just reordering it. X squared times x squared. Whenever you multiply powers, you add the exponents. Base stays the same. Y squared, y cubed, same base, so keep the base, add the exponents. And that's as far as we can go. The -12 is not an exponent, so don't flip. Okay, only negative exponents would you flip to make positive. Now, looking at the fourth one here, there's a lot of negative exponents, and we could deal with that right now. So you could start flipping some of these bases that have negative exponents. And that's perfectly fine as long as you do it right. I'm going to leave them as negatives and manipulate my information, and then at the very end flip whatever. But that's just a preference I have for this problem when I look at it. And that's why it's so important to practice a lot of these. You got to get the properties down, but you are going to have opportunities to do different paths, take different paths than even myself, and we should end up in the same ending point, which is really our goal. So I love that. I love it. And that's why whenever a student, if you ask me like, well, how do I start this? I usually ask, what do you see? Well, I see some negative exponents. Then fix that. I mean, if that's what you see, go for it. If you don't see anything, then we've got to work a little bit so that we can see something. But I see 2 times -7, and I see I'm multiplying these x's, so I'm going to add the exponents. Same with the y's. I'm multiplying these y's, and so I add the exponents, and I get to this point. Now what I see is I see a negative exponent. This stuff is minding its own business. Just leave it alone. But the y has a negative exponent, and so it needs to be flipped, and the exponent needs to be positive, and we're done. Something like that. Okay, moving to a few more examples. I'll bust through these. You go quickly if you would like. Again, this really all 3 of these are going to be very similar to what we just did. I just want to make sure you have plenty of examples. So if you feel like you've got it, just go ahead and skip ahead to the next objective. But in this one right here, b to the 4th, mind its own business. It's positive, but a and c, both of those need flipped. and their exponents need to become +1, which we typically don't put. So there's our answer to that one. Moving to this next one, I'll do -3 times 5, which is -15. My x's, I'm multiplying power, so you add exponents, base stays the same. Y, same thing. I'm going to go ahead and I get y, add the exponents, I get 9, base stays the same. Looking at the bottom one, now here, what we have is a -1 in front. So it's going to be 5 times -1, which is -5. So again, that negative doesn't mean flip. It's a coefficient. Now C's, I have 1 C here and I have 4 there. So when you multiply powers, you add exponents. So we should have 5 of those. And then the D, same thing. What you should get now, though, is D cubed. So there's our answers to those 3. Okay, moving into the next one. Now this one's going to be a little bit easier because it actually makes a lot of sense. It's fairly intuitive once you get the one we just did, multiplying powers. So if multiplying powers, you add the exponents, instincts hopefully will say, well, when we divide, which is sort of like the inverse operation of multiplication, we should subtract the exponents because that's the inverse operation of addition. And so what we want to do is instead of adding the exponents, we're going to subtract them. Now there's a little bit more to that. First off, we have a lot more tendency to try to cancel the bases. The base stays the same. That does not change. So the base stays the same. The other thing to keep in mind is that when I use this property, my resulting base is always in the numerator. Now, it doesn't mean it stays there. I could get a negative exponent, but it is there when I execute this property. And it's always the top exponent minus the bottom exponent. Okay, so make sure it's top minus bottom. Okay, so let's look at a couple of examples here, sort of some basic ones. And so we have p cubed over p squared. And so I notice that I'm dividing common bases. So I can just go over here and say, well, my base stays the same, but I simply take my top exponent minus my bottom exponent, and I'm left with p to the first, okay? Then I look at the 2, and again, this one you could look at 4 over 8, and you reduce it to 1/2. So I know our answer is going to be 1/2, but let's use a property just to make sure. I see that the bases are the same, and I'm dividing. So whenever you divide powers or bases, you want to go ahead and keep the base. It's going to be in the numerator, and subtract the exponents. Now remember, our answer is going to be 1/2, right? So when I get here, this does not look like 1/2. It's 2 to the -1. But now we know what negative exponents and how to handle those. It's flip it. What's the it? The base 2, and that allows me to make my exponent positive. And so there's our 1/2 that we were talking about. Now at the very bottom of the screen, I have a sort of note here. It says, where do you have more? How many more? This is typically how I like to do these type of problems. So I know the property. If I need to use it, I can. And you guys will be the same way. You got to get the property down first. That's the only way that we understand what's going on. But another way of looking at a division one, especially when the exponents are positive, is simply to ask yourself, how many p's do I have on the top? And hopefully you answer is 3. How many p's do you have on the bottom? 2. Where do you have more of them at? The top. How many more? 1. So what I'm trying to get you to do by asking these questions is getting you to the answer of p to the first. It's like canceling out these 2 p's with 2 of those 3. We're left with p to the first. That is how I'm going to end up doing a lot of this. You can even do it over here. I can cancel these 2 2's with 2 of those 3, left with 1. Now, notice I canceled everything out. That doesn't just mean it's 0 up there, it's a 1, but I'm left with 2 to the first power on the bottom. There's our answer. So if that's another way of doing it that you feels comfortable, I think it's a little faster for me. But again, for me to be able to do this, I have to understand why I can do this, and that's the property. So let's go ahead and go through. You can pause, work these, check them, then we'll move on. Hey, but I want to go ahead and do this. I always start, just like I do with multiplication, I start with the coefficients. So 15 over -3 is simply -5, and that's in the numerator. Then I ask myself, okay, where do I have more C's at? So I'm going to go ahead and do it that way. We can subtract. It's not a big deal, but I'm going to do it the way I'm used to, and you guys can either piggyback on that or use the property, which simply says it's C5 minus 2. But I'm going to cancel these 2 with 2 of those 5. So that means that it looks like I have C cubed left on top. Now D's, I have more of them on the bottom than the top, And so I can cancel those 3 and leave 4 of them on the bottom. So I should have d to the 4th on the bottom, which is the right answer. Okay. Working on the second one, very similar. I go ahead and simplify the -2/8, which is -1/9. There's a good chance the 1 is I'm gonna erase it if I have any variables up there. So I'll leave it for right now, but it's probably gonna go away. And so a cubed over a squared, well, that means I can get rid of 2 of those 3a's. So immediately that's going to be an a cubed. I'm going to immediately get rid of my 1 now because it's implied when you have a variable kind of thing. So I have a to the first right there. Now, where do we have more b's at? Top. How many more? 4. And so I should get b to the 4th. And there we have the opposite of ab to the 4th over 9. Looking at the third example, the negative is just chilling. Nothing much there. Y's, where do you have more of them at? Top, how many more? 3. Z's, how many do you have more on top? 2, and boom, we're done. So once you get the hang of this, it goes pretty quick. 12 over 30, let's reduce that fraction. It looks like I could definitely take a 6 out of both 12 and 30. And so I'm left with a 2 on top and a 5 on the bottom. Now, on the x's here, you can use the property. And if you use the property, your x would be in the numerator, and you would do -3 minus a -6, top minus bottom. Okay, and it would work out perfectly fine. That is exactly what the property is telling us we can do. Asking where do you have more of them at, it's a little bit tougher with negatives. Okay, and so I'm going to abandon that. I want to show you actually a third way on this one. I'm going to deal with the negative exponents on this one and flip all those variables. So x to the 6 is going to come to the top and y to the 4th. And x cubed and y squared both have negative exponents, so they're going to go to the bottom. So I'm going to do that. Now, the coefficients didn't change. They don't flip those. They have nothing to do with the negative exponents. But now I can go ahead and cancel, which is what I like doing. So you're going to have 2 on top for sure, and you have 5. And then I can simplify, and I end up getting x cubed on top. And if you notice here, I can get rid of 2 of those 4, so I get y squared on the bottom. And so there's our answer for one like that. Okay. Last thing we'll look at, 0 exponent, something like this. So really what you want to go is anything to the 0 power is 1, except 0. 0 to the 0 is indeterminate. We won't see that, but you'll see it in calculus potentially, but not in pre-calc. So what we're going to have is some base raised to the 0 power. That's not 0. The base is not 0. So it's always 1 is what it is. Now, I can show a lot of maybe a few different ways of why this is true, but let's just go to something like this, something that we just did. When you divide, first off, anything divided by itself is 1. So we're already anticipating this just equaling 1. But if we use the property, what we have is we have 3 minus 3, which is x to the 0. So we already originally said this thing has to be 1 because anything divided by itself is 1. So what that means then is almost like a transitive property, then 1 has to equal x to the 0. And that will apply no matter what the base is except 0. And the reason is 0 can't be in the denominator. And so we have some issues with something like that. Now, just like negative exponents, you want to ask yourself, what has a 0 exponent? So just because, like on this one, just because I see a 0 exponent doesn't mean my entire answer is 1. Okay, that would be an incorrect answer for that one. And so I want to be very careful and make sure I identify what has a 0 exponent. In this case, the base y is the only thing. So the 3x squared stays. But now the exponent doesn't become 1. The entire power becomes 1. So the base to the 0 power, that whole thing just becomes 1. So what we do is it's almost like it's not even there kind of thing. And so you end up getting 3x squared. Looking at the second example, notice if I said what has a 0 exponent, now you can say everything does. So that's the difference between these two. So this whole entire base, the 2x cubed y, is our entire base raised to the 0 power. That entire thing right there just goes to 1. So we'll do a few practice problems here, and we'll wrap up for this first for 1.2a, and then we'll look at more properties in 1.2b. So look at the first example, 3 to the 0 power. Anything to the 0 power is 1, okay, except 0. Looking at the second one, what has a 0 exponent? Just the x. So the -2 is mind its own business. But technically we do this. Now, once you get the hang of it, you won't put the 1 here. What you'll do is you'll just have -2 y to the -4. Now, I'm not done though. because I see a negative exponent. And how do we make negative exponents positive is to flip it. What's the it? The base with the negative exponent. So -2 is not part of the base. It stays in the numerator, but the y gets flipped down to the denominator and made positive. Looking at the third example, I'm going to take care of the fraction first, which is 30 over -3. That's -10. And then, to be honest with you, the y's just cancel, so you're done. They go to 1. So -10 is your solution there. If you use the property, you get y to the 0 because you subtract 3 minus 3. So you still get -10 times 1. Looking at the next one here, I go ahead multiplication. I do 2 times -3, which is -6. And notice that when okay, so here we go. When we multiply common bases, when we multiply powers, we add the exponents, base stays the same. And so we get something that looks like this. And again, you probably could do that a little bit in your head. You get x to the 0. Oh, anything to the 0 power is 1. So it's -6 times 1, or -6. And then looking at the last one, I'm just trying to mess with you guys a little bit. What we have is we have a quantity raised to the 0 power. If that entire thing is the base, then the entire thing goes to 1. So those are really nice problems. And so that's going to be 1.2a, and we will pick up with 1.2b in the next video, which is the remaining 4 objectives in this lesson.